Hello, everyone. All right, just setting up right now, making sure that everything is working properly. So just give me a second here, make sure that I'm up and running. And we're going to be doing chapter 2.10. All right. All right, so the usual rules apply. Just taking my headphones off. All right, I'm going to read through the chapter and then we are going to be doing the questions. So the book, download the book. It's in the description of the video. It's part of the Creative Commons, and it's the Book of Proof, 3rd edition by Richard Hammock. A very good book. Okay, 2.10, negating statements. Given a statement R, the statement not R is called the negation of R. So this is R, this is not R. That negates the statement. Okay, if R is a complex statement, then it is often the case that its negation, not R, can be written in a simpler or more useful form. The process of finding this form written is called negating R. In proving theorems, it is often necessary to negate certain statements. We now investigate how to do this. We have already examined part of this topic, De Morgan's laws. Okay. Captain De Morgan is on deck. Okay, well, there we go. Not P. So this is if you're gonna negate this, this is gonna spread there, and this is gonna get flipped. You could think of it that way. So then what we're gonna do here, we're gonna say not P or not Q. And here, same thing. We're going to say not P or Q. And that's going to give us not P and not Q. All right. So that's how it works. De Morgan's laws. All right. And that's in section 2.6. We're on page 59 right now, if you are following along in the book. Let's see here. Here are some examples that illustrate how De Morgan's laws are used to negate statements involving and, or. Okay, example 2.10. Consider negating the following statement. You can solve it by factoring or with the quadratic formula. Okay. Okay, so let's see here. So if you're going to negate the statement, basically you can say that you can't solve it by factoring and you can't solve it with the quadratic formula. So let's read the first one. You can solve it by factoring or with quadratic formula. And then if we're going to negate that statement, we're saying we want the not version of it. We're going to say you can't solve it by factoring and you can't solve it with the quadratic formula. So in other words, the or becomes an and both of the statements are now negative, both parts. Maybe you can find not R without invoking De Morgan's laws. That is good. You have internalized De Morgan's laws and are using them unconsciously. Example, we will negate the following sentence. R, the numbers x and y are both odd. So let's just do this. Whoop. There we go. Okay. We're going to negate R. R says the numbers X and Y are both odd. And we're going to say not R. Let's do a better R. I'm going to say, by the way, well, first let's write this as P and Q. So this is going to be, okay, so we're going to say, so they're both odd, and we have X and Y, so we're going to say X is odd. And this is working off what they have here in the book. And Y is odd. That's P and Q. P and Q. And now if we're going to negate R, okay, okay, all right. Negating R gives us, let's see here, we're going to say not X is odd or not Y is odd. So, and then also, and then we can take the knots and apply it there, like that. So we're going to say X is even or Y is even. What we did there is, again, we took the knot and we applied it internally, like that. And then another version, what they're saying, another negated R. This is another way of writing it, just syntax. It's the kind of thing, personally, that I would probably be with a more, for me it's more clear, even though it's a little clunkier to say X is even or Y is even, or it's written more formally like this. But I don't know, it just makes this version is serviceable and I like it. All right, and then let's see here. Now let's move on to a slightly different kind of problem. It's often necessary to find negations of quantified statements. For example, all right, not all of X naturals P of X. And then if we were to apply that, I believe it would go like this to apply that. And that would flip to E. So if we did that, exists X naturals P of X. I think that's how it's done. Let's see here. Exist X and naturals. Oh, that are not P of X. Like that. There we go. All right, so let's see here. And if we look at it, if we're saying that not all of X numbers in the natural set have the P of X property, whatever that happens to be, so that means at least one exists, right? If it's not all of them, that means at least one of them. So if we say exists an X in the natural set that does not have the P of X property, because if we take this away, we're going to say all of the x in the natural set have the p of x property. Now we put the not, we're saying not all, so that means some. So if we're saying some, that means it exists one that does not have the p of x property. Okay, so the not has to be just moved to that side, like that. All right, so pretty straightforward. So, and also, if we do this, so we're going to say not exist, or do not exist, x in the set x with the property p of x. So we're saying they do not exist any x's, any x items in the set x with the property p of x. Okay, so in that case, we can also say that all x members of the set x do not have the p of x property. Okay, so this right there. It's in the book on page 60, but you have to understand what's happening here, right? So if we're saying that there do not exist, and the rest of it, what does not exist? The x members of the set x, that's not going to change, right? But the p of x, none exist with this property. So if none exist, well, we don't want to leave the none on the outside. We want to take it inward. The only place to put it is to apply to the property like that. And if you do that, this gets flipped to all. All x members of the set x do not have that property because none exist that do. You see how that works? Yeah. Be sure that you understand the two logical equivalences that conform to our everyday use of language, but they pin down the meaning in a mathematically precise way. Yep. All right. Okay, and we're just flying along today. 2.12, page 61. Consider negating the following sentence. The square root of every real number is non-negative. So, let's see here. The square root of every real number is non-negative. So, symbolically, r can be expressed as all of x containing reals, x squared is greater than or equal to 0. So, what they're doing is all x members of the real set. When you think about like numbers, generally speaking, you're thinking of the real set. So all of the numbers that you generally think of as numbers, they're part of the real set. The more you don't have are like imaginary numbers, surreal numbers, stuff like that. I can't be certain exactly which set the surreals belong to. I haven't worked with any surreal numbers and I've barely touched imaginary numbers. But what I have to say, and then there's all kinds of other numbers and number systems. But what I'm trying to say is that generally speaking, you know, your fractions, your pi, your e, all that stuff, that exists in the real set. Okay, so we have all of x containing the real set. So all of numbers x in the real set. So we pin down what the nature of that is. And then we're going to say, and then we're going to apply a formula to them, which is x squared greater than or equal to 0. So that means this said the square of every real number is non-negative, so greater than or equal to 0. Which, of course, the only way to get 0 is squaring 0. Thus, the negation is, and we're going to negate this. So let's say this is r. These columns. Now we're going to say not r, not all of x containings in the real set, x squared equals 0. And then if now we have the negation on the outside, let's continue further. We're going to say exist x members of the real set which do not have this property. All right, and then let's see here. So that means, and they're going to do one last step here in the book. I need to write my E correctly. This is an M. Let's see here. Go. So this is an existential quantifier, the E. So the E has to be turned backwards, or I call it a turn E also. But yeah, existential quantifier is the technical name for it. So now let's get rid of the parenthesis on the final part. So we're going to say, now we're going to apply that there. So we're going to say x squared is less than 0. Okay? All right. And yeah, so that's the book's example here. So yeah, that means there exists a real number whose square is negative, which is not true in the real set. Okay, so far so good. Now, 213. If a statement has multiple quantifiers, negating involves several iterations of equations 2.8 and 2.9. So those were the ones we did earlier. These ones up here. Those ones. All right, and okay, so let's do this. We have all right. Let's write the statement. S This is a true statement. Okay, so S, the statement says, for every real number x, there is a real number y for which y to the third power is equal to x. So, yeah, that is true. And essentially, the way this can work is you just cube root the y, and then you cube root the x to get the y or the x, whichever number you're looking for. So yeah, basically, but in this case, and this applies to negative numbers. Negative numbers would be fine in this. Right, let's continue on here. Because a negative number can be cube rooted, or because anytime you apply an operation of 3 times, you get back to the -1. Like to the power of 3, you will get back to the negative. So if you take something like, say here, -2 to the third power, right, it's going to be -8. And then if it's going to be -2 squared, well, then that's going to be 4. See how that works? Anyway, so that's good, but 1 second here. Okay, so anyway, what we have next is that I have to write this out. And let's see here, we have for every real number. All right. S, for every real number x, there's a real number y, for which y to the 3rd power is x. So for every, so we have our all. So we have all, we have x, and for this, x is part of the reals, so we have the real set. So what's going to say? We're going to say all x members of the real set. All right, there is a real number for which, comma, I would say exists. There is, so we're going to say exists. So this is like a second part to it. Exists, real number, and then we have the y. Exists, y member of the real set. Now, see how much easier it is when you start like plopping in little bits and pieces? You can kind of start to assemble it like Legos. So, and then you can just, like, eventually you can just read it and just throw it down just like that, you know, like throwing down a glove or whatever. You can just do it. But when you're learning these things, now again, I'm no expert. I'm just saying these are shortcuts that I, as a student, use for a class that I have not passed, that I took twice and had to drop to focus on work. And this would be the 3rd time, but this time I plan to complete the whole book and submit, you know, like, I'm still going to do all the work in class because I'm doing all the odd questions, and the odd questions have results in the back. So we're not damaging the integrity of the book. Anyway, getting off topic. So all of x, members of the real set, for all of those, for every real number x, exists a real number y, comma, and then we're just going to plop the equation. Period. X to the 3rd power, y to the 3rd power is equal to x. All right, so then, so that's a statement, and that's the statement they wrote down here, and we're on page 61. Now, we need to negate this statement. So we're going to call this statement R. I'm just assigning the, actually, hold up. No, we don't want to, it's already S. It's already assigned. I mean, we could do that with R, but it's the same thing. This is simply the mathematical equivalent of what we have in S. So I simply rewrote it. Next, we're going to negate it. Negation of the S. And we're going to write the negation on it. So this is going to be a little tricky, but it's really not that bad. Like, this chapter so far is not really that bad. So, first of all, we threw the parenthesis on it. Next, we're going to figure out how we're going to spread the negation. So, the negation is going to hit 3 points. So, it's going to hit the all, it's going to hit the E, and it's going to hit the equation, right? So, let's do it down here. So, the all gets flipped to the E. And then, okay, and the E gets flipped to the universal quantifier. So the A, in other words, the turn E becomes the turn A. Remember, existential quantifier, universal quantifier, but when I say turn A or turn E as students, it's just easier to visualize it. So turn A flips to turn E, or the turn E turns to turn A whenever you apply a negation to them. And then you have a negation, not a negative, but a negation of the equation. So, and then the way you apply a negation versus like a negative, right? If you do a negative on an equation, so if it's just like, say y to the third power is equal to x, then you can just drop the negative in there, right? But we're actually, a negation gets applied onto the equal sign. So it does not equal to in this case. Or, yeah, so we can just do that. We can just drop it in here, and then it's going to be y to the third power is not equal to x. That should do it. Yep. Let's just finish writing all this down. Okay. So we have, make sure, did I finish it correctly? Let me check my work here with their example here. With all of our, yep, looks right. Yeah, I mean, it's pretty straightforward. There's not a lot of, fussing here. You just have to know where to apply it. Now, what they did, I applied it, let's see here. They applied it in steps, gradually shrinking the parenthesis. I applied it to the first. In other words, we see where the commas are, so we can have like 1, 2, and 3, and you can gradually shrink the parenthesis. And you can go like this, and then you can go like that. Each time progressing the negation, or I guess you can do like I did. The result's the same. All right, good. So the negation is a false statement and can be written either of the following ways. Not S. So yeah, there is a real number X. So exists real X. There is a real number X such that for all the real numbers, y to the third power is not equal to x. So yeah, that's how it's read, and you can write that out if you wanted to, but essentially it's right there in the proof. In writing proofs, you will occasionally have to negate a conditional statement if P implies Q. The remainder of this section describes how to do this. To begin, look at the expressions. All right. We're going to say not P. I'm guessing it's going to flip their direction. Oh, I see what they're doing. Okay. So if it's not that, no, that's right. We did this. It's been a few chapters, but so if you negate the P implies Q, we're going to say P and not Q. So not P implies Q. We're going to say it's P and not Q. And the proof, we did this, I don't remember. It's maybe 2.4, 2.5. But it was definitely in there. We just created a truth table. By now, we should be fairly comfortable with truth tables. And here we go. Section 2.6. If you want to watch the video, that was an exercise where we did that to prove that this is equivalent. Which, we can do, but we're at this point, we're going to try to get through this section here. Let's see here. Negate the following statement about a particular constant, number A. Okay, so we have R. If, so we have an if-else. If A is odd, or if then, if you have an if then, that's an implication. Then A square is odd. If A is odd, then A square is odd. That's a false statement. So that means right here we have if then is a P implies Q type of statement. Now we need to negate this. We need to say not R. Okay, and how will we do that? Well, first, actually, before we negate it, let's actually write out R mathematically. So let's see here. We're going to say let's see here. If A is odd, then A squared is odd. A is odd implies A squared is odd. Okay. Yeah, let's see here. We're going to say R not, and we're going to say A is odd and not A squared is odd. Okay, so P and not Q. A is odd and A squared is even. So not R. Perfect. A is odd and we're gonna apply the negation, and we're gonna, remember, you have to, whenever you apply negation, it's not a negative sign. You have to understand what you're negating. What you're, by a negation is, it's like flipping, right? It's flipping like a coin flips, or stop and go, that kind of a stop. It's an inversion. You can think of it that way. You know, when you have an odd, you want to, if it's not odd, then it has to be even. It's whatever property you're negating. It has a binary nature where it has a black and white side. In other words, one side is white, and you said it's not white, therefore we know it's black. Or if only, you know, like certain lights, they don't have a yellow, they just have red or green. You could say the light is not red, we know it's green. A binary nature, if you negate something with a binary nature, it gives you instantly the knowledge of what is the current state. So by negating it, we're going to say A squared is even. Now that is a true statement. So we're going to say here, yeah, and notice that like when I applied the negation, it disappeared, but it didn't disappear, it just made it even. So we're going to say A squared is odd and A squared is even. So that's the negation of R. In this case, what they wrote, they said their negation, their version was A is odd and A squared is not odd, which you can think of it that way. But again, not odd is even. It's a binary nature thing. All right. This example is like the previous one, but the constant A is replaced by a variable X. We will negate the following statement. If X is odd, then X squared is odd. Hang on a minute. So, in a minute here, what they're doing. All right. So they're going to go with this here, the book. Page 62, we're going to say R. All right. If X is odd, then X squared is odd. Okay. So now what we're going to do is, let's see here. For all of X members of the integers, why integers? Why is it not the reals? Right? The integers are a subset of the real set. However, if we said reals, that would imply fractions. Things that don't have the odd or even property. Odd or even refers to whole numbers, and so what happens is it's a binary nature thing, but it has to only be whole. So it is a characteristic specifically related to the integer set. So whenever we talk about anything that's odd or even, we're instantly talking about the integer set and only the integer set. Now, you could constrain the real set to just the odd or evens, but that just makes it that much harder on yourself. you're basically saying we're working within the real set, but only using the integer set. So it's just like, why? It's just extra steps. All right. So we're working in the real set. Now the R is not the real set. Just to be clear, what I just said, that tangent I went on, that's the real set. Okay? This right here is an R and it's an assignment R. These two are not the same. So these two are not the same. All right, so now let's do this. We have, for all of x integers, let's see, we're going to say, and then, comma, x is odd, or we can put ox, actually, we'll do that next, which implies x squared is odd. Now I'm going to take a page out of this book and do something that they did before. Here's another way I can see us as writing this thing. It's something they did earlier. We're going to say O implied O. So just to be clear, make sure that, see, like, yeah, I'm just going to put these down here. So, yeah, we can do that. Now, the reason why this is, I mean, I guess it'll save us a step in a sense, but because we're using turn E's and O's can be confused for zeros, it's sometimes just simpler to have it this way, just have the odd and even written out, the word, instead of putting all this down. All right, let's negate R. All right, so we're gonna, let's do how they did it last time. We're gonna go by every comma. Although, no, I actually probably don't need to do that. Because we just have an implication here, there's only one comma. So let's just do this x, all of x, containing the integer set. Which implies squared is, let me think about this for a second. Let me think here. All right. If we negate this for all, right. Just to be clear, not P implies, we don't negate the P. Remember that. That's where I had a minute of thinking there. P and not Q. We end up negating the Q. Our P remains as it is. So the not R, we're going to take this and we're going to apply it to here and to here. No, I don't know what I'm talking about. We're going to apply it here and there. There we go. But not on the P. So this is P, this is Q. All right. So, and of course, the implies becomes a not. The implies gets dropped. So let's do that. So exists an x integer where keeping the x is odd. X is odd. That's the P. That does not change. And the not hits the odd part. That's the binary nature. And x squared is even. Okay, exists x integer where x is odd and x squared is even. A true statement. Okay. Now, what they did here is they kept the not, which is fine. You can do that. Again, the truth values of what we're saying here remains. Everything, whether I write it my way, where I completely got rid of the not by essentially filtering it through all the way, and they simply choosing to leave it a little bit in there. It's as long as the not, as it filters through the statement, it has to hit its particular points. And you can stop at any point. You could just leave it there and say, no, I just want that there. But the truth value will not change if done correctly. So here's what they did. Let me next show you. So they filtered through the E. The turn A becomes a turn E. So the universal quantifier becomes the existential quantifier. X is odd. P is not changed. The implies is dropped in favor of the and. They filtered through that. Then we're going to say not x squared is odd. That's the point where they chose not to filter it through, which is fine. It's whatever. If you want to leave it like that, that's fine. Okay, so and the statement, if you want to translate it, is there is an odd integer exists. This is our odd. And this is x is integer. Exists odd integer. Exists odd integer. Let's see here. Whose square? Well, in this case, the and is just rewritten kind of as whose square is not whose square is not odd. Okay, yeah. Okay, alright. So far, so good. Notice that R is true and not R is false. And the above statement showed how to negate a conditional statement if P implies P of x implies Q of x. This type of problem could sometimes be a more complex negation. And its solution. Okay, let me think here. Notice that R is true and not R is false. There is an odd integer x, like 3 for example, whose square is not odd. Okay, so yeah, right. Whose square is even. Okay, so because you're multiplying a number by itself, you're so actually I don't know what the rule is, but yeah, if any number that's well, actually let's do a direct proof. So let's just say 3. It's an odd integer. Squared is 9. It's not even. So basically here we go here. X is odd and x squared is even. So this is not even. So remember, the negation was false. The original statement is true. So this is a true statement. And another one, we can say 5 squared, 25. 13 squared is 169. 11 squared is 121. So, yeah, I guess you can just like, what is 25 squared should be 625. I think it's 625. Let me check that one. Yeah. Okay, good. So yeah, as you can see, the numbers, what we do here with our, I don't know why exactly. Like, this is not a proof. This is simple. I mean, it is a direct proof in the sense that we just have to prove one because there exists, right? So watch this. What we're saying here is that if x squared is odd, then here. Oh, where is this here? Yeah, if x is odd, then x squared is odd. So if we think about that if else is a little hard to prove because it just applies to all of them. So if you try to direct proof, you'd have to prove every number, which is impossible. Time aside, it's just infinity. You would have to do like a more general statement, or you can try. This is why we would try to like reverse it in a way to rewrite it to where it could be easier. We can prove later on. We'll be doing like things like proof by contradiction. Say like try to prove that the opposite and show that there's a contradiction of that. Why it wouldn't work if it was even, and we would start by like defining what an odd number is and then using that definition. By definition, this is like mathematical. It's like, an even number can be defined as 2 times any number. So like for a 2 in the integer set, so like 2a. A would be the number that you want to put there. Times 2 will give you any even number. So a could be 1 times 2 gives you that 2. That's an even number. 2a gives you, if a is 2 now, it gives you 4. Anyway, getting off topic, we'll deal with that later in future chapters. Well, so far so good. Let's do some questions. All right, let's see here. The number x is positive. Okay. We have to negate this. Number okay, so we're going to say call this R. The number x is positive, but so just negate the sentence. The number x is positive. Well, let's see here. We're going to say x is positive. And y is and 1 minute. We're going to say both are positive for the minute. You're going to see what I'm doing. There we go. X is positive and not y is positive. So remember what we talked about, how we said P implies Q, and the not of P implies Q is the not is also P and not Q. So why don't we just reverse the order? So we want to negate the negation. So we have this form right here. We have this form right there. P and not Q. All we have to do is negate the negation. P and not Q. So what I'm going to do now is I'm going to do this. I'm going to take the P and not Q, put in a parenthesis, and I'm going to convert this inside. I'm going to do this. I'm going to convert it into the not form. Again, this is the same thing. I can just flip back and forth with these. They have the same equivalence to truth value. So I'm just going to flip it right now. So I'm going to have another parenthesis suddenly appear because that's associated with that form. So now I have not P and not Q. A double not. We'll cancel them out. So now we have P implies Q. This is a negation of the statement of that form. P implies Q is a negation of the statement above. So what we're going to do now is we just establish what P and Q is, and we just write it. So we're going to say, now, if, there we go. That's the form, if then. If P, then Q. That's our form. So all we have to do, the number X is positive. That's going to be our P. So we're going to say, if the number X is positive, then the number Y is, a minute here. So I did the negations. The only thing is, see here. So I did the Q. We had the only thing is that not P implies Q. Let me just check on my work here. So I took the Q. P implies Q. Okay, so the forms are fine. The only thing is that I have to still take the nots and apply them to the sentences, because the sentence, well, the form, the if then is correct, and the P will not be changed. I still have to take care of the Q. If X is positive, then the number Y is, so we're going to, the X is positive, and we're going to say here, one second, let me check my work here. And, oh, right. Because, so we had, P and not Q. And if we had not P, if X is not positive, so the, see, so like with sentences, like what I wrote there all makes sense. It would be easier if I was working with characters. Now I have to mentally do the same flipping of the English. All right, because I don't want to mess this up. So let's start at the beginning. Not P implies Q. The number X is positive, but the number Y is not positive. So I have here X is positive and not Y is positive. So that's our form here. Now, if we were to flip this, then to the implies not P implies Q, that would mean that we're going to have here P implies Q. And we're going to say the not P implies Q. We're going to say we need P, not X is positive. And then we're going to say implies, let's see, what was it? So yeah. And, oh, this is going to be here on both. Not implies. So the not, this part disappears. Yeah, not Y is positive. Positive, okay? Make sure I did this right. So I did that. I pulled that out and converted that to P implies Q with the not existing on the outside now. So the X is positive and the not and the Y is positive. X is positive implies Y is positive. Should have the same value as X is positive and Y is not positive. Hang on a minute. Oh. Right, sorry. Not X is positive implies Y is positive. So if we say not X is positive implies Y is positive. So yeah, that should be that. And then if we have that not, then we're gonna, now we go down here, we're gonna say not x is positive, which implies y is positive. Okay, and then we're gonna drop the nots, and then we're gonna say x is positive implies y is positive. If the number x is positive, then the number y is positive. Number x is positive, but the number y is not positive. And we're negating this. Yeah, I think that's correct. Let's find out. Okay, so let's see here. The number x is y is not positive. The but can be interpreted as and using De Morgan's law. The negation is the number x is not positive or the number y is positive. So they did with the number x is not positive. What does that look like? Not is positive or y is positive. Okay, that's the correct answer. Let's see here what I wrote here. If the number x is positive, then the number y is positive. And it's not x is positive or y is positive. So x is either not positive or y is positive. And if you look at De Morgan's laws, so what I attempted to do here is with the double knots and then try to negate that from there. I don't know. Didn't quite work. I'll figure that out. Let me think about this for a minute here. Why? It's probably because of the implication. Let me look at the De Morgan's law. So the number x is positive. The but can be interpreted as and. I see. That's where I went. Okay. So what I did could have worked, but I know why it didn't work now. When you have the word but, it could be interpreted as and. So this is the correct one. We wanted to negate this. Negate. So first of all, the first statement here is actually P and Q, right? That's all it is, P and Q. And to negate that, negate P and Q, you're going to get not P or not Q. So in that case, where I went wrong was I went with the implies. So what I said could have worked if it was a statement where it was P implies Q. If the statement read, if the number x is positive, then the number y is not positive. So if that's the case, so if the original statement read, if the number x is positive, then the number y is not positive. And if we negate that, we're going to say, if the number x is positive, then the number y is positive. So that should work. And that's negating of P implies Q. So it wasn't what I did with using the negation of the implication. It was the fact that I didn't see it as P and Q. All right, but that's solved. Let's go. Right. 3. Okay, so we're going to define this as R. Wrong R. R. So this is going to be our statement. Or actually, you know what? Let's use S for statement. S. And we're going to say for every prime number P, there is another prime number Q with Q being greater than P. For every prime number P, there is another prime number Q with Q being greater than P. So that sounds like a true statement, because if you start at the first prime number 2, then there is 3. And yeah, the primes go on infinitely. So there's always going to be, any prime that you pick, there's always a bigger prime than that. It just means the numbers go on forever. Basically, what that statement tells you is the prime numbers, they go on forever. However, they do have a starting point. Or you could think of it as that way, because you can't say the opposite. You can't say for every prime number P, there is another prime number Q where Q is less than P. That's not a true statement, because you just start with the first prime. If P is the first prime, then Q cannot be a prime and be smaller than P. All right. Remember, primes are defined as any number that is a whole number that is divisible by 1 and itself. So, in other words, like if it's 3, it's divisible by 1, it's divisible by 3. If it's 5, it's divisible by 1, divisible by 5. If it's 13, it's divisible by 1, it's divisible by 13. You see how that works? Anyway, let's see here. For every prime, okay, for Q exists, okay, that is, hold on, I'm gonna look at the, a while back, this is probably in 2.1, okay, there is a list of the terms. Okay, here we go. So, this is, you have to find the specific form of it. Here we go. Page 44. If P, then Q. Nope. For Q, it is sufficient that P. For P, there is another. Let's see here. For Q, there is another P. Now, by the way, they might be throwing us off with the numbers P and Q's. In this case, we're not talking about primes. We're using P and Q as in statements, P and Q. We're going to say, for every P statement, we're going to say exists a Q statement. All right. So we're going to say for Q, it is sufficient that P. Nope. For P, if P, hang on a minute. Yeah, I have to really, the important thing is to get the form right. Maybe it's like a double implication here. Let me see here. Okay. The other thing is, maybe I should think of it differently. Let me try it differently. Let's rewrite this as mathematically as we can. Okay, we're going to say all P exists exists Q. Okay, so all I'm gonna say P for all P. How do we define a prime though? Let's see here. Okay, well, let's define this. Okay. You just have to negate the statement. We don't have to actually write this whole thing out. I might be overthinking this. So, okay, but the actual, fine. Let's just, without going too crazy here, all P is prime, comma, exists, Q is prime, comma, such that we have Q greater than P. All right? And this form, we just, remember what we talked about? So this is our S statement, and we're going to negate the S, and then we're going to spread it out. We're going to say the negation on parenthesis. We're going to say all P is prime, comma, exists, Q is prime, comma, Q is greater than P. Okay, and then we're going to negate that. So we're going to spread the negation here, and here, and right there. Okay? Not S. We're going to say all becomes exists. P is prime for all Q is prime, comma, where Q, now we flip the sign. We don't just flip it though. We have to go with, it's going to be greater than or I think. We have to add the equivalence to it though. Let me think about that for a minute. So if you are negating, so if like we're going to say 2 is greater than 3, we can negate, how will we negate that? We're going to say 2 is greater than 3. 2 is not greater than 3, so that means if it's not greater than 3, it can be less than it. But if it's equal to it, that's also not greater than 3. So we're going to keep the equivalency there. All right. So let's read what we got so far. I think we're getting somewhere. All right. The negation is exists a prime number P for all prime numbers Q, where Q is less than or equal to P. Exists a prime number P for all prime numbers Q. Any Q number you want. There's always going to be that one prime that's greater than or equal to the Q. Hang on a minute. For all. That is, now let's read the first statement, not the negation. For every prime number P, there is a prime number Q with Q being greater than P. So if we have number P, now, if one of these statements is true, then the other statement has to be false. That's what I'm trying to figure out. So the first statement, there is for all prime numbers P. Well, let's just pick 2. Is there another prime number Q where Q is greater than P? Yes. What about another number? What if P is 3? Then Q would be 5 or 19. Then that's fine. What about our statement? Exists a prime number P for all prime numbers Q, where P is greater than or equal to the Q. Doesn't sound like a negation. where P is maybe that's the problem, is I might not need to flip that sign. Exists prime number P for all prime numbers Q where P is less than or equal to Q. How does that sound? Exists a prime number P for all prime numbers Q. Now, exists prime number P for all prime numbers Q with the prime number Q. So this P will always be bigger or equal to any Q number. That's also a true statement. But it's a negation in the sense that we flip the P's and the Q's. Because now the P is the bigger one. I don't know. I think this might work. Let's find out. Okay. Let's see here. There exists a prime number P for which P is greater than or equal to Q for every prime number Q. Yeah. Okay, so I answered correctly. There's a prime number P such that for every prime number Q, Q is less than or equal to P. So again, in this case, is there a prime number P that's going to be bigger than any Q number that you have? That's a true statement. But so you think that, like, remember I said earlier that one has to be true and the other one's false? This actually works, but in the sense that because we don't know what the P's and Q's are, we could just assign them. They could just as easily be the same number. Like in the second one, in the first statement, the Q and the P cannot be equal to each other. They cannot be the same number, but in the second one they can. So in that sense, the statement has been negated. You could think of it that way. And also, with the P can now be bigger than the Q and so forth. So that's where the negation's about. All right, let's continue. Okay, and that, by the way, let's see here. All right. Okay, I'm just trying to find. There we go. Page 62. That's where we're at. This was 3. Let's do the 5. Okay. All right. For every positive number E, there's a positive number M for which formula? Okay. Right. Let's do that. We're going to call this statement S. I'm going to say for every positive number E, epsilon. That's epsilon, by the way. There is a positive number M. Whenever you see the word for multiple times, you could think of it as a comma. It's a good way to think about it. You're adding on additional statements. Now, you got to be really careful with what I just said there, by the way. You have to understand context. It's like when you're talking about the English language, context is everything. Also, just like, for instance, just like the word. Let's see here. That's how I meme the other day. Okay, Pacific Ocean, right? Sound with an S. Sound. Shin, like that. See how that works? Pacific Ocean. That's a CH. Shin. So notice how the C in the word Pacific Ocean creates different sounds. But I mean, it has to do with, you have rules, right? You know, it's like because of the kind of letters, or in this case, the vowels A, I, and O are the reason why you're creating this kind of effect. Anyway, just a neat little thing. A little off topic, but what I'm saying is context when the English language is everything. You have to know what the vowel will do. You can't just say, well, you know, the C will always make a C sound. No, it's vowels, context. That's what I was trying to get at. All right. Okay, and here, for every positive number epsilon, there is a positive number m, for which formula here, function of x, the absolute value of f of x minus b is less than epsilon whenever x is greater than m. Epsilon. Never greater than m. Okay. So for every is for all. I'm going to say here E is positive. There exists. And so, and now, by the way, we can define the set, we narrow that down, but we could also just write epsilon is positive, because we're not trying to fully convert this into symbolic logic. We just want to rewrite the statement and negate it. There is a positive number m exists. There is, it exists. Positive number m. So we're going to say for every positive number e exists a positive number m. And then comma, formula. Whenever x is greater than m. We're going to add two formulas, probably. It's probably something like this. Okay. Let's try it right here. For all positive, for all positive epsilon, comma, exists positive m, comma, and then we're going to say the absolute value of f of x minus b is less than epsilon whenever x is greater than m. When we're not gonna negate that part, I think. Let me see here. Yeah, I have to be careful at this part. This is one that could trip us up. X is greater than m. That last part, I have to think about that part. Okay. And if we're gonna S negate this, we're gonna start by, we're gonna say exists positive epsilon for all positive m, And then the formula here, you know what? We are going to flip those signs. Let's flip some signs here. Okay, so we're going to take the absolute value of f of x minus b, and we're going to flip that sign to, we're going to say that's greater than or equal to epsilon whenever x is less than or equal to m. All right, that's how I'm reading it. So let's find out. For all of epsilon, so they defined it in the real set. I just wrote positive epsilon. Okay, epsilon is greater than 0. So I wrote positive epsilon. They wrote epsilon is in the real set and it is positive. Now, in this case, we didn't have to fully write it in the... hold on. I'm reading the reading the wrong section. I'm sorry. Hold up. Of e 0 infinity and exists m 0 to infinity, x is greater than m, which implies, oh, whenever means implication. Okay, but let's so here's the thing. They wrote it out fully in the math. Let's I first want to know if I answered it correctly. Working out the negation, exists positive epsilon for all of positive m, and we're going to say not x is greater than m, implying the function of let me see, hold on here. Whenever, okay, not, looks like I did it right. Yeah, I think I did it right because they just not the original statement. And if you not the original statement, x is greater than m, yep, I said it's not. So yeah, I answered it correctly as far as I can tell. I'm going to write it out in full symbolic logic here, what they did. Yeah, let's just write out the whole answer. It appears, though, yeah, that all they did was... the first parts, they agree. They just defined what positive means and the domain of it. Which, again, is not necessary. They're just saying it was helpful to solve this. In terms of the equation, they just went not... and then they wrote like this. Except, and let me just move this around a little bit. Whenever is another word for implies. So we're going to say, let's see here. X of m. Now, the one thing is, hang on a minute here. Whenever... now, because of the word whenever, you have to be careful, though. Even though it's put last, it defines. Remember, an implication is cause and effect. So the cause says whenever that happens, that's the cause. The cause is the whenever. X being greater than m is the cause. The formula is the effect. So what they did was this. They did x is greater than m, which implies... here we go. The absolute value of f of x minus b is greater than epsilon. Okay, so they wrote it out. Again, don't have to do that, but they did it because, like they said, to negate this, it may be helpful to first write in symbolic form. I'm just showing you what it would look like in symbolic form. X greater than m implies the function f of x, absolute value of f of x minus b is less than epsilon. Now, if you want to negate that, all you got to do is you just have to drop the negation in there, and you can leave it at that. So, if you're going to negate it, here like this, not. The only thing where let me just check one more thing here. Pn not q. P. See, I did a double negation. That's technically where I went wrong. I'm looking at this thing. If you negate P implies Q, then you get P and not Q. So what I did was this. So let me just do a slight, hang on here. They did P, they negated the, oh, actually, hold on. So they wrote us out, which this is fine. That's fine. But because it's an implication, the negation, the P stays, and the P is this. This is P implies Q. So the P should not have been changed. That was my mistake. The rest of it holds up. There. Okay. So exists a positive epsilon for all positive m's where the f of x is minus b is greater than or equal to epsilon whenever x is greater than m. Basically, that's what they did. Now, if you wanted to fully do symbolic logic, because this is, here we go here. You can write this whole thing out. Let's just add another page here. It's getting a little tedious here. Let's go here and here. Okay. Right, let's do that real quick. So we're going to write this out just because this is a great exercise. We're going to define this as S. Epsilon there is a okay, so for every, so we're going to say for every, this now we're going to go symbolic. I'm going to go for all, we're going to say epsilon is, let's see here. For all epsilon, now the way they did it here is they constrained it, and it ranges from 0 to infinity. And now this right here is, it's open on 0, so in other words, does not contain 0. Right. Okay. So, and 0, by the way, it's not positive or negative. It's just 0. I believe, though, 0 is considered even just because of where it falls in the system of odds and evens. Because you have 2 is even, 0 or 1 is odd, negative 2 is even. All right, so here we go. So we constrained it. It's open, and infinity is also open on the other end. And then also we need to add the fact that So basically we just define this. Epsilon is positive, and it ranges from 0 to infinity. So for all epsilon containing, that's containing, by the way, it's different. So, and that's from 0 to infinity. That's why I wrote positive, but they wrote that way. That's fine. We're going to say exists M containing also ranges from 0 to infinity, comma. And now we have the, remember, whenever, the word whenever is a cause. Whenever I go to the store, right? Let's say, whenever, okay, let's just say this, yeah, whenever light turns green, no, again, that's, an example was very clear about, okay, well, I'm just overthinking this. Whenever you see the word whenever, it means that something is the root cause of it. And if you have a root cause and you have an effect, the key is, it's about P and Q. P is the cause, Q is the effect. So this is the P, even though it comes last, right? You have to look at what whenever refers to. It doesn't, whenever is not referring to the formula, it's referring to this. So if that's the, now we're going to write this as P implies Q. So we're going to say X greater than M. And we're going to say implies formula here. Let me move this over. Okay, f of x minus b. I'm still running out of space. B is x minus b is less than epsilon. Okay. So, let's see, make sure this is correct. So this is the symbolic logic, and this is how they wrote it out. Now, if we're going to negate this, negate S, we're going to negate all of this for negating all epsilon contains. First, we're going to just write this out. Now remember what things can be negated, what can't be negated. We're not negating the fact that it's positive in this case, although we're negating the words every and exists. So it doesn't mean that, in a sense, we are negating positive and negative because we're going from every positive number to there existing at least one number, kind of a situation, which is a negation. So I'll add another parenthesis because I put one up here. So now we're going to spread this out. So we're going to say all give for to exist. Exist in epsilon, that's positive. So instead of flipping the definition of the epsilon, we're flipping the number of epsilon that exists, so to speak. So in a sense, yes, we're still negating the positive aspect of it. It just means that it's not every anymore. And now the M, we're saying all of them now, all positive M instead of just at least one existing, right? And then we're gonna have, so if you negate P implies Q, it's Q and not P. Result. So we're gonna say negation of P implies Q, which is equal to P and not Q. That's what that gives us. Let's see here. Just double check that. P and not Q. Right. So then we just have to negate this. So we keep the P keep the cos, and we're going to say and not f of x minus b absolute value is greater than epsilon. And we can go further and apply the negation inside at the epsilon. Or we can just stop there. Let me see here. Yeah, that looks right. Negation has spread through it, so I don't need the full parentheses anymore. All right, make sure I did this right according to them. Exists epsilon that's positive for all of m that's positive. And they're saying not. Okay, so what happened with them was that they just left it right here. They left it right there. And what I did was I did the bottom one, not Q. And if we wanted to further spread this out, we would put it right there. So it would be like this, x greater than m. And we're going to say f of x minus b is greater than or equal to epsilon. Like that. So we can do that. And it just, because that is, yeah, that all works. That's not Q. Or you can just leave it, yeah, but it's whatever. You know, they left it out here. You can put it here, or you can put it here. You can just apply it here, like that. So let's just kind of keep that in mind. All right. So that was 5. Again, the answer was exactly the same as what I wrote, except the only difference was that I did a double negation on the P implies Q, and that's the key. The P, I should not have done a negation of it, which is this. This is the P. That's the one that I negated by going like this. And aside from that, everything matches up. This is just more symbolic. But yeah, we just have to write out the answer. Okay. Right. It's, okay. All right. Okay, cue that clip of Onion Man screaming, "I'm vegan." Yeah, I've been around the internet a long time. I don't eat anything that has a face. Let me grab some more coffee. It's 12:30 now, and I gotta be at work at 7:45 tomorrow, so not gonna get that much sleep tonight, but that's okay. I still want to get through this chapter. So I got the extra coffee. Okay. I don't need anything with a face. So that's... we're going to define that as S. Okay, so we're going to say... I don't need anything that has a face. I eat anything that has a face. Yeah. Okay, sure. Not S. I don't eat anything. Oh, okay. I eat everything that has a face. I eat everything that... I don't eat anything that has a face. Anything is the E, and we're going to switch it to everything, which is turn A. So turn E to turn A. So we're going to say, and the negation to the not, we're going to apply this. So we're dropping the don't. Eat everything. That's pretty horrible. That has a face. So you should get that condition looked into. Everything. Literally everything that has a face. Okay. Now, let's get that looked into. Oh, hang on a minute. I will eat some things that have a face. Note the answer, I will eat anything that has a face. That is wrong, both morally and mathematically. Okay. So I answered incorrectly. So anything, right. Anything is not E. That's incorrect. It is actually turn A. So it's universal. Anything means universal quantifier. And the universal quantifier has to be turned into some things. So that's because anything, that's what tripped me up. So basically, it's, yeah. I eat some things. Anything is, so what I did, my mistake was this. I mistook that for the anything as in existential quantifiers, the turn E, suggesting that it's any one thing. But the problem is the any is the key part, makes it universal quantifier, the turn A. So I just kept the turn A, which was wrong. So I corrected that now to the turn E, existential quantifier, some things. Okay. So yeah, that's the answer there. I like that. I was more offended by the being wrong mathematically than morally. Okay, here we go. I found that more morally repugnant. Although I guess that's a double negative. Being less morally offended at. Okay, I'm just going around in word loops here. Okay, if sine x is less than 0, then it is not the case that 0 is greater than or equal to 0 and greater than or equal to pi. So this is unit circle, or the sine wave. If sine x is less than 0, negative x, so then x will not range between 0 and pi. Okay, sure. Well, we'll get to this in my algebra and trigonometry book. I want to power through chapter 3. Just go nuts with it, and then I want to start hitting the proofs in part 2. Once we get to part 2, I'm gonna unlock the calculus front and continue with the algebra and trigonometry front. So yeah. Right now, let's just do this. 9. If else, sine, if p then q then. If sine x is greater than 0, so this is going to be p. P implies q, implies then it is not q, implies not q. Then it is not q. Then it is not the case that 0 less than or equal to x is to pi. Okay. So we're going to say so we have p implies q. This is the not, and this is q. Okay, let's take these two out. So if P implies not Q, that means it could also be P and a minute. So if we're gonna negate that, if we're gonna negate this, we're gonna have to negate both P and Q. So we're gonna say not P implies Q. Is that the correct? Well, yeah, it should be the correct, because if you wanted to negate it, right now we have P and not Q, like this. So if we're gonna negate that, all right. How would that spread though? Should I flip the sign? If sign, okay, well let's just see if we can negate this. Let's see here. S. So we have if sign x is greater than or equal to 0, comma, then it is the case. So all we're doing, we're dropping the not. Then it is the case that, now in this case, remember how I said we would have to flip the equations? Well, in this case, that is the Q, and the not is just the word not. So it's the case that 0 is greater than or equal to x, and x is less than or equal to pi, the range of the sine wave in this case. What happens is that's Q, and we don't have to go in and start taking it apart from the inside. We just have to drop the not. That, at least that's how I'm interpreting it. We'll know in a minute. You know, as always, I'm hit and miss with these solutions, but I'm confidently wrong. So yeah, when I'm wrong, I'm confidently wrong. Anyway, when sine x is, by the way, that's probably one of the key to being a politician. It's okay to be wrong as long as you're confident about it. Not that I'm running for politics. That's not my game. If sine x is greater than or equal to pi, so we flip that, then it is the case. All right. Okay. Okay. No, the Morgan's laws aren't going to help us here. This is an if-else. This is an implication. Suppose. All right. Yeah. No. Then if P then is a statement, the statement is true if it's impossible for P to be true. I'm just looking at previous chapters. All right. Yeah, it's what I think is gonna work. Let's find out. If sine is, there exists a number for x for which sine is 0, and 0 is let's see here. If sine, this is a complicated one. I think here. I mean, it's not that complicated. Just got to work it out. If sine is, for which sine is and, I'm just trying to understand how they did this, where they placed it. So we had if P. So we had if P then Q. If P then not Q, so we just did the negation of the Q, I guess. If P then Q. I think that's what they did. Yeah, that's all they did. Okay. What I got wrong was my negation of it. I did the not cause in. Let me see here. Okay, I think this is, yeah, when I did the negation, I should have left the P alone and done this. P implies Q. Should have dropped that across. So if I did that, now word for word what they did. Okay, if sine x is less than 0, then it is the case that, and yeah, that's the inverse of that. What they wrote was this. There exists a number x for which sine x is greater than or equal to 0 and 0 see here, less than or equal to pi. So they're saying there's at least one number. They're adding E exists. And I said if, yeah, all right. Let me see what form they use. So let me go back here. All right, that's what they did. I see what they did. Okay. This is what I was trying to work out. I was like, what form did they use to where they got it this way? And the form they used was this. They went with all of x, members of x, comma, p of x. That's the form that they went with. We're going to say this. The x is right here, right? That x. And all of the numbers that are less than 0 makes the members in the set x. And then we're going to say then p of x, the case right here. Okay? So now, if you want to negate this, if you're going to, let's see here, if you're going to negate all of x containing set x, p of x, in that case, what you do is you get exists x with that membership and not p of x. So they did the not, but we already had a not in there, so the two canceled out. That's how they got that situation. So that's how they went about doing that. So this would have taken a bit more thinking on my part. But it's like one of these things, if you get a question wrong, don't just be like, okay, well, I got it wrong, and this is the answer. I'll just try to memorize the answer. That never works. Instead, you have to like suss it out and figure out where was the divergence between how you came to your answer and how they came to their answer. Where was the book trying to go, so to speak? That's the important part, because if you could trace back that trail and then find your way to how the book wanted it, then making the mistake's not really a mistake. It's just a learning process. See? So that's how you get forward. You keep moving forward. All right. 11. Okay. You can, let's see here. You can fool all the people all the time. So all of the people all of the time. And then let's see here. Let's see here. So if we're going to flip that, we could flip it as you can fool some of the people some of the time. I think that's how to flip it. You can say you can fool all the people some of the time. No. Why don't we use what we just did? Yeah. So we're saying you can fool all of the people. And then so we're going to say X people set X and then P of X people you can fool that's how I'm reading it. So if we use this form, I'm going to say all of the people belong to the set of people that you can fool. And we're going to say X, and we're going to say P of X. Okay? So basically we're saying that actually another one, fact 2.2 and 2.9. If X is a set of, say, all the people, and Q of X is a statement, and for our case, it will again be people you can fool about X all the time, the following statements mean the same thing. All of X, members of X, Q of X. Or X members of the set implies Q of X. P implies Q. That might be, okay, all right, so let's try this. So instead of P of X, we can call this Q of X. So if this is going to be this, it still takes the form of P implies Q. So we're going to negate this as... But you know what? What's the other form we can have this? This means let's see here now. Or what about... Well, you know what? I'm gonna undo what I just did. I'm gonna try it this way. Now, let's see if this is S. Let's try negating S. So to negate it, we're gonna say a negation of all of our members of X and P of X, which is equal to negation of S, which is equal to there exists members in the set X who you can not P of X. So, and we're going to say this exist people you can fool exist people you can fool not all the time. Let's try that. I'm going to fix the English in a second. Can fool not all of the time. Exist people you can fool some of the time. There. The time. I think that would be the correct way to do it. All right, let's see. Okay, there are answers. It says several ways to negate this, including there is a person that you can't fool all the time. Exist people you can fool not all the time, so that's what I wrote. Not all the time. So when I rewrote that into some of the time, that's understood to mean not all of the time. When you say some, you're saying some portion of it, but not the whole. You can, when we say some of the time, it means not all of the time. Just so that we're clear here. So yeah, I answered correctly. There are versions that they gave us, just some of several, of course. There are several ways to negate this, including there is a person you can't fool all of the time. Now, I went with exist people. Probably more accurate would have been here. I defined X as people. They defined X as person, and then the members are people you can fool. So let's just clean that up just a little bit. All right. As we're gonna say, what else did they give us? Yeah, they because people are members of the set X, the single is the person. So there exists full. And to emphasize the point, the emphasis here is, again, this is an English language thing. We want to emphasize what we're trying to get at so that the meaning isn't lost. So I'm going to add the word only. There exists a person you can fool only some of the time. So that is more accurate. Exist person. Again, this more has to do with it just not sounding clunky. Exists a person you can fool not all of the time. So, and that goes with what they wrote. There is a person that you can't fool all the time. Or there is a person X and a time Y for which X is not fooled at time Y. Oh, that was clunky. Okay, only some of the time. Alright, you can't fool. So the way you negate this, you could either say can fool, but you have to say some of the time, or you can say can't full, but then you have to say all of the time. You can't use both negatives, of course. You can't say you can't fool them you can't fool them some of the time, because if you can't fool them some of the time, that means you can fool them all of the time. I mean, this is like getting a little into the weeds, but it's important for stuff like this. So yeah, that's cleaned up. All right, that was that. Okay, somehow we survived that. Now we have 2.11 logical inference. Okay, hey, look at that. That's it. We just have to read through about 2 pages worth. 111 and 112. Okay. So 112 is just like an author's note. It emphasizes importance on certain things. It doesn't necessarily like add anything new other than just emphasis. And yeah, there are just a couple of small points on 11. So yeah, tomorrow looks like we're gonna start on counting. Yay! We're gonna learn how to count. I'm excited. All right, I hope you enjoyed it as much as I did. Now I gotta get to bed and then go to work tomorrow. Have a good night.